Good morning, everyone. Myself Devika, working as assistant professor in the Department of Electrical and Electronics Engineering at Sri Muthukumaran Institute of Technology. Today we have discussed the subject on MR3452 Control Systems Engineering for 2021 revisions. We are going to learn the topic root locus technique in 4th unit of Control Systems Engineering. Introduction. The placement of closed loop poles plays a crucial role in shaping the system's transient behavior. The three characteristics of control systems is how these pole locations shift in response to changes in the controller gain, making it essential to measure and analyze these shifts. So this session introduced the concept of the root locus. Overview. Imagine a feedback system arranged in a closed loop featuring a straightforward controller. So, figure 1 diagram of a closed loop control system. The system incorporates a gain parameter denoted as K, which can be adjusted. Understanding root locus. So, consider the straightforward single loop system depicted in figure 1, which is governed by the characteristic equations 1 plus kg of s equal to 0. Here the parameter k is adjustable. So the root locus represents a graphical plot on the complex S-plane showing every possible position of the closed loop poles as the system parameter. Every point along the root locus satisfies the characteristic equation, which can be expressed in its polar form for deeper analysis. Definitions. So the root locus graphically represents the locations of the closed loop system's characteristic equations, roots, as a single system parameter, like the open loop gain is varied. This technique reveals how the system's poles shift across the complex S-plane in response to changes in one control variable. Then, distinguishing root locus from Routh-Hurwitz. The root locus techniques reveals how the poles shift across the S-plane as the control parameter varies, providing a detailed trajectory of the locations. In contrast, the Routh-Hurwitz approach identifies the specific ranges of the control parameter for which all poles remain to the left of a designated vertical boundary in the S-plane, ensuring system stability within these limits. Analyzing the roots of a characteristic equations, for example, considering a position control servo mechanism as our system of interest. The system includes a servo motor coupled with a load, both regulated by a controller through a power amplifier. So the open loop transfer function is given by G of s equal to K into S plus 2. The open loop poles are located as S equal to 0 and S equal to minus 2. That means P1 is equal to 0, P2 is equal to minus 2. The closed loop transfer function can be expressed as G of s equal to K divided by S square plus 2S plus K. So the system characteristic equation is S square plus 2S plus K is equal to 0. So the stability of the second order system is ensured when the parameter K is positive. The system's relative stability is influenced by the position of its poles given by S equal to 1 and 2 equal to minus 1. So the exact location of these poles varies depending on the value of the gain. So this gain K corresponds to the open loop transfer function's amplification factor. Challenges of using the direct substitution method for root locus. So plotting the root locus by directly substituting various values of k into the characteristic equation becomes increasingly complex for higher order systems. So to make the root locus construction more manageable for these complex systems, a set of specific guidelines has been developed. Guidelines for root locus constructions. To sketch an initial root locus diagram, a set of guidelines has been established. We will explore these guidelines by first presenting each root, then explaining why it holds true, and finally illustrating it with an example. So for rule 1, being by identifying the open loop poles and zeros on the complex S plane. At starting point where where the gain k equals 0, the closed loop poles and zeros coincide exactly with the open loop poles and zeros. The root locus plot is always mirrored symmetrically along the real axis. So the roots of the characteristic equation can be purely real, purely complex, or a purely mixture of both types. Then rules for constructing the root locus. Rule 2. Determining the number of branches in the root locus. For example, considering g of s, h of s is the open loop transfer function of a closed loop system, that p represents the count of open loop holes and z denotes the number of open loop zeros. Important, each root locus branch originates at on open loop pole and concludes at on open loop zero. The total number of root locus branches n equals the greater value between the number of finite open loop poles and finite open loop zeros. When p exceeds z, n equals p, and the difference p minus z indicates how many branches extend toward infinity. Conversely, if z is greater than p, n equals z with z minus p branches starting from infinity. Then guidelines for plotting the root locus rule through explain. So a point on the real axis belongs to the root locus with the total count of open loop poles and zeros located to the right of the plane point on the real axis is an order. Example, give the transfer function g of s equal to g of s into h of s equal to 1 divided by k into s plus 1, s plus 2 into s into s plus 3, s plus 5. So guidelines for plotting the root locus rule 4. Consider transfer function. Identify the segments on the real axis that are part of the root locus. Breakaway points. If breakaway points occurs when multiple roots coincide at the same location for a specific gain value k. Consider the example g of s equal to here. Here the roots s and s minus 1 and s minus 2 originate from the open loop poles and converge to the points p1 is equal to minus 1 when k equal to 1. At this breakaway point, s equal to minus 1 as k increases beyond 1 towards infinity, the roots split into complex conjugate pairs. Such a location where two or more roots meet for a particular gain is defined as a breakaway point. Then guidelines for root locus construction. Rule 6. The points where the root locus crosses the imaginary axis can be identified using Raoult's stability criterion. Then portions of the root locus may lie in the right half of the complex plane, signaling potential system instability. Then the exact crossing points on the imaginary axis define the boundaries of system stability. By substituting the gain value k found from the auxiliary equation into the system, we can pinpoint the intersection of the root locus with the imaginary axis. Then guidelines for constructing the root locus. Rule 7. So rule 7 determine the departure angle from complex conjugate poles and the arrival angle at complex conjugate zeros. Each branch of the root locus originates from an open loop pole. So when dealing with a complex open loop pole, we compute the angle of departure denoted as pi of t. So the formula for the angle of departure pi of t is equal to 180 degree minus pi. So p represents the total angle contributed by all other open loop poles related to the poles in quotients. Pi of z is the sum of angles from all open loop zeros measured at the same pole. Advantages of root locus: simple visualization, stability analysis, design tool, no need for complete solutions, and insight into the system behaviors. Disadvantages: limited to scissor systems, manual plotting complexity, approximation errors, difficult for higher order systems, and only gain variations. Applications: it is used in control system design, stability analysis, transit response improvement, electrical and electronic systems, mechanical systems, and aerospace engineering. These are the reference for the further study. Thank you.